In today's class, first and foremost, I'm going to talk about the dynamics and stability. So I'm going to discuss concepts in dynamics and stability. So first and foremost, when you study dynamics, we always start with Newton's laws. So Newton's second law that all of us studied in high school is force is equal to mass times acceleration. Please note, force is a vector, which means it has magnitude and direction. Mass is a scalar. Acceleration is also a vector. So whenever you have a vector quantity, coordinate system is extremely important. What does it mean? So it means that if you have an object, and then if the force acting on object is F, which is in the same direction as positive x-axis, this force is positive. Now, if this mass accelerates in the same direction as positive x-axis, this acceleration is positive. So the case here is your force is positive, mass is a scalar, no positive or negative, and acceleration is positive. So this is very important. So your force is positive, acceleration is also positive. This is called as Newton's law in translational coordinates. Translational coordinates, which means you can have force in x direction. Force in x direction is going to be Fx is equal to max. You can have force in y direction. You can have mass ay, and you can have force in z direction, which is maz. So you have three forces and three accelerations. Mass is a scalar quantity. There is another variation of Newton's law, which is Newton's second law in rotational coordinates. So rotational coordinates. So when you talk about the rotational coordinates, you all know this equation. Force in the translational coordinate gets replaced by the torque in the rotational coordinate. Again, torque is a vector. Mass is replaced by a mass moment of inertia, which is a scalar quantity, and the angular acceleration. So this is called as the torque. This is mass moment of inertia. And last guy is the angular acceleration. Now, I just want to tell you that this is not emphasized, but this torque is equal to I times alpha. This equation is valid only at 3 points. So which means I give you a case wherein what you have is you have an object, okay? You have an object. And this object has mass moment of inertia I. And its angular acceleration is alpha. Okay, it has mass moment of inertia I, and it has the angular acceleration alpha. Now you can apply P is equal to I times alpha. this equation only at when it's a fixed point, when it's a fixed point. So if you have a hinge, you can apply T is equal to alpha when it's a fixed point, or it's a center of gravity, CG. And the last case, when the velocity vector is parallel to the displacement vector, but that case does not arise in robotics. What does that mean? Is T is equal to I alpha is condition is only valid at point O and at point G. You cannot apply T is equal to I alpha at some random point over here, some random point over here. If you want to look at T is equal to I alpha, where T is the torque, then you need to take the moments about a point. Remember, torque or the moments, or for that matter, alpha, I is about the point. Now let me define what is moment of inertia. Moment of, let me start with what do I mean by inertia. Inertia means laziness. So basically, if someone has a lot of inertia, that means we are lazy. Now, moment of inertia, the inertia, Newton's law of inertia says, if the object is in motion, it will continue to stay in motion. Object is at rest, it will continue to stay at rest. That is the natural tendency. We don't want to change our state that easily. We are resistant to change. Same thing, mass moment of inertia is how difficult or how easy it is to give a moment or create a moment or create a motion about the point. So for an example, mass moment of inertia is given by an expression which also defined I is equal to mass times the radius of gyration, which is mass times the radius of gyration. So if you have a pendulum, and say you have a mass at the end, if this radius is L, mass is located at the end, the link is massless. So I for the pendulum is, and again this is going to be I at O, IO for the pendulum is going to be mass M times the radius of gyration square, ML square. Now, radius of gyration is similar to the concept how far the mass is from the point where it is rotating. So, another example is if you have M significantly larger, the mass moment of inertia is large. If you have a small mass at far away, the moment of inertia is going to be large. Now, I want you to think about something extremely important, and this is a very practical insight. And you have seen this. I just want to make you aware. So, moment of inertia is mass times the radius of gyration square. So, this is where the mass is located. This is where the point of rotation is, and your torque is going to be about this point O. Your torque is going to be about point O. You agree with me? Now, if you have a pendulum wherein the payload is significantly higher, or a robot, the payload significantly higher, then clearly the moment of inertia for that robot will be significantly large. So if your payload is farther from the pivot point, very important. If your payload is farther from the pivot point, then your moment of inertia will be large. What happens if your moment of inertia is large? If your moment of inertia is large, then the amount of torque that you need to supply to get that robot moving will be significantly large. You agree with me? Now I want you to think about how DuBot Magician is constructed. For DuBot Magician, the first revolute joint stepper motor is vertical at the base. You agree with me? The second joint stepper motor is again very close to the base. You agree with me? Third motor is not at the joint, but again it is very close to the second motor. You agree with me? And the reason for that is if you, and again, most of the robots would have some type of a linkage or some type of a drive mechanism so that they minimize the load at the joint. Because if you add the motor at the joint, the overall weight of that robot would be same, but the mass moment of inertia would be significant. So the idea is, many a times you would see that the motors or the heavy objects are located at the base so that the mass moment of inertia is minimized. Everyone understood this? So that is what we have seen in DuBot. You would see the same thing in lot of industrial robots, and then you will see the 4-bar mechanism or a pulley drive or a bell drive, maybe, or a chain drive, some type of a drive mechanism that is driving the joint. Now, the next thing which I want to talk about is if you have a mass and then if there is a spring, you have the spring mass system. The spring has stiffness K, mass has mass M. Stiffness K is given as load divided by deflection, which means if you have a spring, if the spring can be easily stretched, it's called as the soft spring. So if the spring can be stretched easily, it's called as the soft spring with stiffness very low. If the spring is hard to stretch or compress, if it is hard to stretch, then it is called as the hard spring and K is higher. So this is basically stiffer and lighter. So you have a stiff spring or non-stiff spring. Load divided by deflection is given as Newton per meter. Now what I'm going to do is I'm going to apply a force. I'm going to apply a force. You agree with me? Once I apply the force, this mass would travel. This mass, let's say it travels by amount X. Do you agree with me that this spring would get stretched? The spring will be stretched by amount X. You stretch the spring, so what you have, and then what you do is you kind of pull the mass and let it go. So what's going to happen is you have this spring applying the force, which is K times X. The spring is applying the force, which is K times X. And the mass is accelerating in this direction. So you have the spring, which is pulling the mass, and you have the acceleration because you kind of give it a jerk, you pull the mass and you apply the force and remove the force. So mass is trying to move forward and spring is trying to push it back. So on this mass, you have the spring force acting in the left direction. So I'm going to apply force is equal to mass times acceleration. So mass is m, acceleration is in the positive x direction. So acceleration is positive, and I can write this acceleration as the second derivative of displacement, which is m x double dot. Spring, the force given by spring is going towards the negative x direction. So this is going to be minus k times x. So the total, this equation looks like mx double dot plus kx is equal to 0. So this is the equation for the spring mass system. Now what would happen? So please try to understand, there is no damping. It means you pull the mass, let it go. Let's just imagine this thought experiment. This mass is on the frictionless surface. There is no friction of any kind. There is no friction of any kind. Do you agree with me that this mass would continue to oscillate back and forth? So it will go on here, then it will continue to oscillate back and forth, and it will go like this. Do you agree with me? If there is no energy dissipation, these oscillations would go on for the infinite amount of time. Now, what I want to do is, what I have here, extremely important, force is equal to mass times equation, or mass times acceleration. Once I substitute the value of force, once I substitute the value of acceleration, it involves second derivative, which means this is the differential equation. This is the differential equation. Why it's a differential equation? Because it includes the derivative. Now it is extremely important to understand this differential equation has x, which is a function of time. X, which is a function of time. If I take the second derivative of first derivative of x, I get velocity. If I get the second derivative, I get the acceleration. So in other words, t, which is time, is the independent variable. And x is the dependent variable. So x or x dot or x double dot is the dependent variable. Now what I want to do is, I want to solve this differential equation. I want to solve this differential equation. What do I mean by solving a differential equation? Solving a differential equation means, how do you solve an equation? As long as the left-hand side of the equation is equal to the right-hand side of the equation is solved. Whether it's an algebraic equation, whether it's a differential equation, or whether it's an integral equation. As long as the left-hand side, whatever you have on the left of an equal to sign, is equal to the right-hand side, left side is equal to right-hand side, the equation is solved. Do you agree with me? Now what it means is, I need to find out. How I find out is up to me. I need to find out this function x of t. Please understand, this is the function. This function depends upon time. When I substitute x of t here, and I take the second derivative of x of t, get x double dot t, and substitute it over here, if my sum total is equal to 0, that is the solution of differential equation. Everyone understood this? What is the solution of any equation? Solution of any equation is you try to find out a number or a function. When you substitute that in the equation, the left hand side of the equation is equal to the right hand side of the equation. Everyone understood this? Please note, m is a constant. 1, 2, 3, 4, 5. A is also a constant. 1, 2, 3, 4, 5. So the only unknown is x of t. X double dot of t depends upon x of t. So what we should do is we should find out somehow what is x of t. Everyone understood this? Now, if you look at this plot, I'm going to show you that this is the time axis. This is the time axis. This is x. So you can see that this motion of the mass is sort of sinusoidal, or it is repeating. It is periodic. You agree with me? So how do you just quickly, how do we solve these equations? When there are very few equations, you can solve them by hand. Most of the equations are solved using trial and error. It means you use some type of a numerical technique. Now the next fun part is the entire differential equation source. Okay, I'm going to explain in 5 minutes. If the differential equation is linear, what do I mean by linear? Linear means one burger for $1, 2 burgers for $2. It means no. This is mx double dot. It is kx is equal to 0. It is not kx square. It is not mx double dot multiplied by x. It is not mx double dot multiplied by x dot. It means it's linear. Can you see this is a linear term? This is a linear term. There is no square. So this is called as the linear differential equation. M is a constant. K is a constant. So this is called as linear differential equation with constant coefficient. So this is called as linear differential equation with constant coefficients. Now, next thing I want you to understand, the right hand side of this equation is 0. You agree with me? The right hand side of this equation is 0, which means there is no external forcing on this equation. So it is unforced. So no force. So unforced. Because the right hand side is equal to 0. So unforced. And I promise you, in your differential equation class, you have studied only this type of equation. Maybe you actually looked at the forced equation, but that's also very simple. And I can show you how you can solve it. Whenever you have a differential equation which is linear and that has constant coefficients, whenever you have a differential equation which is linear and constant coefficients, there is only one thing that you should do. You need to, how do we solve differential equations? By trial and error. There is only one trial you need to do. You should write x of t is equal to a constant a e to the power lambda t. No matter what equation you get, as long as it's a linear equation, its and differential equation, its solution is given as a e to the power lambda t. Lambda is a constant, a is a constant, e to the lambda t. Why am I using e to the lambda t? Because exponential function is a periodic function. So I'm assuming I may be incorrect. I'm assuming that maybe this function would help me get the solution of this differential equation. That is the only thing that you should remember. Now then, you take this equation to your x of t is a to the e to the lambda t. X dot of t is going to be constant a. What is the derivative of e to the lambda t? Lambda e to the lambda t. X double dot of t is again second derivative a lambda square e to the lambda t. Do you agree with me? At this point, please try to understand. The only thing I know is m is a constant. M is known. K is known. Please note a and lambda are unknown. The only thing that I know is since lambda exponential function is periodic, repeating, so I would use this. Now I'm going to substitute equation 2. I'm going to substitute equation 2 in equation 1. So can you see this becomes m lambda square e to the lambda, so, and there is a here, e to the lambda t, a plus k e to the lambda t a is equal to 0. You agree with me? Now, can you see from here, a cancels out, a cancels out, e to the lambda t cancels out. So this term, this term, this term, this term, everything gets cancelled. And what I get is I get m lambda square plus k is equal to 0. Do you agree with me? Now, what that means is lambda square is equal to minus k by m, which means lambda is equal to square root of k over m I. Do you agree with me? Now, let's start with what we started with. I assume the solution of that differential equation x is equal to a to the e to the lambda t. I substituted this in that equation and I found out that the only way that equation 1 can be satisfied when my lambda is equal to square root of k over m, which means I have found out the solution of the differential equation. Thus, solution of differential equation, the solution of differential equation is extremely important, is x of t is equal to a lambda e square root of k by m I times t. Are you with me? And that's it. This is the solution of the differential equation. Now, some of you may ask me, what happens here? Please note, there are two routes that are possible. So you can have plus square root of k over m, or you can have minus square root of k over m. So you can actually make this even better, a1 plus a2 e to the square root of k by m I t, which is negative sign. So now this is nothing but the total solution of this differential equation. Now, some of you may ask me, but we haven't figured out what is A1 and what is A2. Once again, you agree with me that equation number 1 has two derivatives. If you have two derivatives, how do you solve the differential equation? You have to integrate it once. You have to integrate it once again. So you get the solution of an equation that has two derivatives. So you have to integrate it twice. Do you agree with me? You integrate it once, you get one constant. You integrate it twice, you get the second constant. So these values, A1 and A2, are nothing but the constants of integration. So A1 and A2 are the constants of integration, which means A1 and A2 depends upon the velocities and displacement when time t is equal to 0. So what you need to do is to find out the value of A1 and A2, you have to solve something called as the initial value problem. It means what is the value of displacement, what is the value of velocity when time t is equal to 0. Everyone understood this? Now, at this point, I want to address a very important concern. Notice that the equation that I have, includes this imaginary term. Do you agree with me? I. Now, but if you look at the physical system, if you look at the physical spring mass system, it's not imaginary. It's a real displacement. So how do I relate this imaginary I that appears in mathematics, the actual displacement that has some physical meaning? Okay. And that is a very, very important question that I want to address. So before we go there, I want everyone to remember whatever you studied in your differential equation class can only be summarized in one sentence. If you are solving linear differential equation with constant coefficient, I can tell you you spend half of your class doing that. You haven't solved the system where mass is changing, k is changing. You haven't solved the system when you have x multiplied by x dot, x squared. So you have not dealt with nonlinear systems. You haven't dealt with time varying systems. So whenever you have a differential equation that has constant coefficients and is linear, that is the standard risk. Substitute x is equal to a e to the lambda t. Take that equation, find how many derivatives that you want to find. At the end, equate left hand side of the equation is equal to the right hand side of the equation. Everyone understood this? And solve. However, the problem that you are going to realize, we got this lambda imaginary because lambda square was minus k over m. You take the square root of minus k over m. You get square root of minus 1 and plus and minus square root of k over m. So in other words, you have two roots. You have lambda 1 is equal to plus square root of k over m I. Lambda 2 is minus square root of k over m I. In other words, if you substitute in this expression, if you substitute this part, and I want you to try this, but imagine a2 is equal to 0. If you substitute xt is equal to a1 e to the lambda the square root of k over m by it into the equation 1, left hand side will be equal to right hand side. If you just take this part of the equation, substitute that in the first equation, left hand side will be equal to right hand side, which means this part solves the differential equation. This part solves the differential equation, and the superposition principle in linear system says that if you have A solution satisfying the equation, you have B solution satisfying the equation, so the total solution is A solution plus B solution. Everyone understood this? That is called as superposition principle. This is the solution of the linear system. This is the solution of the linear system. The total solution is the first solution and the second solution. Everyone understood this? That's all you need to remember from your differential equation class. Now here comes the engineering part. When we dealt with mathematics, we got all these imaginary numbers. But our displacements, our velocities, our accelerations are real. You agree with me that mass is actually moving. So how do I relate this imaginary expression to the actual expression? So basically the solution what I'm seeing here, that has some real part and imaginary part. Remember, whenever you are left with a complex solution, separate out the real part, separate out the imaginary part, and solution will be clear. Remember I said that life is complex. As long as you separate out the real part and imaginary part, you will solve the problem. Now, let's do that. I'm gonna say k square root of k over m is equal to lambda. I'm gonna say square root of k over m is equal to lambda. Just to make it my life easier, a1 e raised to lambda it plus a2 minus lambda it. Do you agree with me? I'm going to write that. What? Lambda is square root of k over m. Did I make a mistake? What? Oh, I think this is okay, right?
You just forgot to write the A to E.
Oh, yeah. Oh, I forgot to write E. Okay, sorry. Yeah, okay. Now remember Euler's formula, e to the I theta is equal to cosine theta plus I sine theta. Do you agree with me? Now I have a complex equation. I'm going to separate out the real part and the imaginary part, a1. So I'm going to say this is going to be cosine lambda t plus I sine lambda t plus a2 cosine minus lambda t, which is going to be again cosine lambda t, and sine of minus lambda it is going to be minus I sine lambda t. You agree with me? So I had a complex equation. I separated the real part and imaginary part. Now what happens? I'm gonna collect cosine and I'm gonna collect sine. Do you agree with me? If I collect sines and cosines, I get a1 plus a2 cosine lambda t plus I get ai minus a2i sine lambda t. Now what is a1 plus a2? A1 plus A2 is a constant, which is C1 cosine lambda t. What is A1I minus A2? Again, this is a constant, C2 sine lambda t. Thus, what you have is you have an equation that represents the real solution, because C1 is the constant that depends on displacement. C2 is the constant that depends upon the velocity. What it means? Or it means that you have this mass going back and forth, performing simple harmonic motion, and the simple harmonic motion comprises of a sine component and the cosine component. Magnitude of cosine component depends upon the initial displacement, and magnitude of sine component depends upon the initial velocity. So these are the two constants, and this is the real solution of the differential equation. Everyone understood this? Okay. Now, since you studied linear algebra before this class, I will try to explain this in the context of linear algebra. So you have this equation mx double dot plus kx is equal to 0. What I want to do is, I want to represent this equation into a matrix equation. So I want to express this equation in matrix equation, which is also called as state space. So how do you find out the state space? So state space, you start with the first variable that has zero derivative. So the variable is xt, and then you use the first derivative of this guy, which is x dot t. So please note, this state space includes x of t and x dot t, because the highest derivative here that is appearing in this equation is x double dot. So this equation has two state space variables. State space is the technique of representing the differential equation into the set of first order differential equation. So this is a second order differential equation. I'm going to represent the second order differential equation in terms of a set of first order differential equations. So the state space comprises of displacement and comprises of velocity. So I'm going to write this equation something like this. Do you agree with me? D by dt of x is equal to x dot. So this is x and this x dot. Do you agree with me? D by dt of x dot is x double dot. Do you agree with me? X double dot is nothing but minus k by m times x. So I can also write this equation as minus k by m x. So in other words, this first order equation can be written as d by dt of x is equal to 0x plus 1 x dot d by dt of x dot is equal to minus k over m x plus 0 x dot. And I want you to confirm what I've done is correct. So I have an equation mx double dot plus kx is equal to 0. That is the second order ordinary differential equation.
I'm representing it as a set of two. The first relationship is within the state variables. My first state variable is x. My second state variable is x dot. So d bar dt of x is equal to x dot. D bar dt of x dot is x double dot. And that x double dot is nothing but minus k over m x. So if I want to write these two expressions in a matrix form for linear algebra, if I want to solve this equation into matrix form, what I have is I have x dot d over dt is equal to 0, 1 minus k over m 0 x dot. So this is called as two first order equation. Everyone understood this? So your equation is now written as in the linear algebra form, x dot is equal to a x, where x hat is nothing but x dot transpose. So what you have is you have this matrix equation. Agree with me? Now here comes the problem. How do we solve a matrix equation? If this equation was a scalar equation, okay, scalar means no two rows, just one equation. So let me write this down. X is equal to a, so x dot is equal to a xt. So a is a number, maybe 1, 2, or 3, whatever. A is a number. How would you solve this equation? If you want to solve this equation is dx by dt is equal to a x of t. Take all the excess on one side, dx divided by x is equal to a times dt. Do you agree with me? Then integrate both sides. The integration of dx over x is natural log of x. Integration of a dt is at. I'm gonna take the exponential on the both side. So I get x of t is equal to e to the at, e to the at, e to the at. This can be written as e to the power a multiply e to the power t. A is a constant. Do you agree with me? A is a constant. So since a is constant, I can write this down as a e to the t and x of t. Do you agree with me? E to the a. So this equation is the solution of the differential equation. So basically a e to the at. Actually, I can write this down. E to the at. Oh, once I solve the, I have a constant of integration. Sorry, I forgot. E to the at plus a naught. So plus e to the a naught at. So I made a mistake here. Please try to understand. When I integrate this, I'm this equation happens ln of x is equal to e to the at plus a, and then when you take the exponent on, no, sorry, I made a mistake here. This becomes at plus a naught. At plus a naught. You take exponent, so what you have is you get a to the et and a naught. And a naught is a constant a, and you get e to the at. Now, please try to understand, if a is equal to 0, if a is equal to 0, you have x of t over here, you have t over here. If your a is equal to 0, your solution is going to be constant. Solution will be a. So this will stay as a. If your a is negative, if your a is negative, then your solution is going to look like this. A is less than 0. And if your a is greater than 0, then your solution is going to look like this. Now, what it means is the behavior of the solution depends upon the sign of a. The behavior of the solution depends upon sign of a. When a is less than 0, the solution is asymptotically stable. If when a is equal to 0, it is neutrally stable. And when a is greater than 0, it is unstable. Now, I want you to focus for a second this equation and this equation. The solution of x dot a x t is nothing but logarithm of a. So the solution of x dot t, which is a vector equation, is a matrix logarithm, so which is Lm of matrix A. So basically you get multiplied by t. So what you do is, if you want to solve the same equation using matrix formulae, then what you do is, instead of using the scalar logarithm, you can use the matrix log. And when you use the matrix log, you will be able to solve the matrix equation. However, depending upon the eigenvalues and eigenvectors, this matrix log may or may not exist, and there are different techniques that you can use to solve this matrix logarithm problem. Now, if you were to find out the eigenvalues of this matrix A, if you were to solve the eigenvalue problem, if you try to solve the eigenvalue problem, which is determinant of A minus lambda I, let's do that for a second. So if you solve determinant of 0 minus lambda 1 minus k by m, and then you are going to have minus lambda. So please try to understand. You will notice this eigenvalue problem is going to give you lambda square minus k by m. That gives you lambda square plus k by m. And this is the exact same equation. Lambda square is nothing but minus k by m, and then lambda is equal to square root of plus minus k by m I. So please understand, the way we solve the differential equation, whatever answer that we got for the equation for lambda, the answer that we got for the equation of lambda, that is nothing but, so this equation is nothing but the eigenvalue problem that you study in linear algebra. This is nothing but the same eigenvalue problem in linear algebra, and this is what you get when you express the equation using as a matrix equation. Now, there are a couple of things if I want to discuss, but I'll stop here and we'll continue in the next class.